Moving on to concept 4, main concept 4 is this is kind of I like this one. This is kind of a cool rotational equivalency. It's the rotational equivalency of mass, um, and just as more mass makes something harder to speed up or slow down, harder to accelerate. That's Newton's second law, right? F equals ma. Rotational inertia makes something harder to speed up rotationally. So you can imagine. Let's pick. Let's pick a like a bowling ball here. So you got a ball, a solid ball, and uh, if you want to spin it about an axis to the middle, kind of like the Earth, for example, what's going to be easier? By the way, is it going to be easier to spin a bowling ball or to spin the Earth? Just picture yourself trying to speed up the Earth rotationally so that instead of 24 hours a day, it's 20 hours a day. Let's shorten the day by 4 hours for the fun of it, right? What's going to be easier to accelerate that much? Well, they're both spheres, and you can't really probably see it here, but this is 2/5 mr squared. So the rotational inertia of this sphere depends on both mass and radius. Obviously, the mass of the Earth is more, so that's a given. It's going to be harder to spin that. But the radius is larger too, and radius actually makes a larger difference than mass. And so that's going to make the Earth much harder to accelerate rotationally than a bowling ball. Uh, you can picture, you can try something out. Take a meter stick in the classroom and try to spin it back, try to rotate it, grab it by the middle, and try to swing it back and forth rotationally, and then maybe tape some objects. Actually, why don't you do this? Yeah, tape like some objects close to your hand, so close to the center of the ruler, and try to rotate it. And then tape those objects near the ends of the ruler and try to rotate it. You haven't changed the mass of the ruler and whatever you tape to it, but you've just changed the location of the mass. In the second situation where you tape it at the ends, you've moved the mass farther away from the center, and you should notice that that's going to be harder to rotate. So anyway, rotational mass depends on both how much mass and the distribution of mass, which is this squared component. And different objects, different shaped objects have different rotational inertias. I did a thin rod here because you see that a few times in your web assignment problems. It's 1/12 ml squared, where L is the length of the rod. That's actually this middle one here, if you rotate it about the very center here. Whoa, didn't want to do that. If you rotate it about the very center, right here, it's going to be 1/12 ml squared. So the longer the rod, the harder it is to rotate. The more massive the rod, the harder it is to rotate. But you got a bunch of other objects too. You got a hoop, which is just basically I equals mr squared. You got a cylindrical ring, which has two different radii, so it's got some thickness here, whereas this was just an infinitely thin sort of hoop. And so this is the rotational inertia of one of these. You don't have any problems using this one. This shape. A solid cylinder is like a soda can, for example, rolling down a hill, is 1/2 mr squared. A solid cylinder like a soda can rotating around, so like spin the bottle type thing, is way more complicated than just rolling down a hill. It's 1/4 mr squared, where r is the radius, plus 1/12 ml squared, where L is the length of it. Notice L doesn't play a role in this. It can be infinitely long and it still will rotate just as easily if it has the same mass. Thin rod, this can be like a meter stick. A meter stick is considered like a thin rod. Thin meaning like infinitely thin. It has no radius, and so a meter stick approximates that. A solid sphere like a bowling ball versus a spherical shell like a basketball, which is hollow on the inside. Another hoop, but this time the hoop is rotated around like this, like if you were to spin a ring on the table, versus roll a ring. This is like rolling a wheel, and you have a perpendicular slab. So look on page 253 for these. You don't have to memorize these. And yeah, Now notice all of these are rotating through the center of mass of each object. The axis is going through the center of mass, right? So think about that. Now what happens if these rotate not through the center of mass? So for example, if you take a meter stick and instead of spin it around the center, you like put the meter stick on the floor, standing up like this, right? And then you drop it so that it just falls down like that. It's still rotating, but now it's pivoting at the end here, not at the center. So how do you handle that? Well, there's a theorem called the parallel axis theorem where the rotational inertia of the meter stick is the original one if you were to rotate it about the center of mass, which are these formulas here. You can think of these as all ICOM, COM, right? Plus mh squared, where h is the distance from the center of mass to the pivot point. So h would be that distance there. Or if you wanted to spin the ball, instead of rotate it around the center of mass like that, you rotate it on the edge so that it sort of wobbles around, like, or makes almost like a donut shape. Then h would be the radius here. If you wanted to make a true donut, let me see if I can find a picture of that. Found one. All right, so here's the here's a torus. So you can imagine taking a sphere, right, and moving the sphere around here so that the pivot point is actually here now instead of in the center of the sphere, like here. That makes what's called a torus shape, kind of like a donut. The parallel axis theorem, the h in the parallel axis theorem would be the distance from the center of mass of the sphere, which would be right in the middle here, to this new pivot point. So anyway, hopefully that gives you a good idea what h is. This is useful because isn't that interesting how you don't change the shape of the object, you just change how it's rotated, and that changes the I, the rotational inertia. It's pretty interesting. Ice skaters do this, right? This is actually more of a topic for the next unit when we talk about angular momentum, but they change their rotational inertia by putting their arms out versus holding their arms close to their body. They can change their rotational inertia and spin differently because of that. But anyway, torque. So if you want to apply a force to cause something to rotate, then you need to, then that's called a torque. If you want to open a door, you can try this. Go to a door and try to open the door by pushing really close to where on the door to where the hinges are. You're gonna have a hard time opening the door because your radius is really small. Even though you're applying a large force, you have a small radius, so you're going to get a small torque. And in order to open the door, you need to apply a reasonably large amount of torque, right? So there's two ways to do it. You can either increase the radius from the pivot point where you're pushing, or increase the force. If you decrease the radius, you're going to have to increase the force, which you can probably feel when you're trying to do that by, what was I saying? Anyway, and there's another aspect to it. This is a cross product. And so the angle matters. If you were to, so here's a door, right? It's a horrible door, but you get the idea. And you want to rotate the door this way, right? So it swings out that way. So you want to apply a force perpendicular to the door to get the most torque. If you push like right into the door, right in towards the hinges, the door's not going to rotate at all. If you push slightly in, the door will rotate, but it'll be hard to rotate because most of your force is being wasted pushing into the door, whereas only a small component of your force is perpendicular rotating the door. You can see that on here, right? If you want to rotate this record, think of this as a record from the top. If you apply a force out, you're not going to rotate it. If anything, you're just going to pull it away. But if it's like stuck in the record player, this is not going to rotate. If you want to give it the full rotation, you'll apply a force perpendicular or tangent to the circle, and anything in between is going to give you less of a torque. And so you can see from F1 we have components. The radial component, which is wasted right here, that doesn't give you any torque, and the tangential component, which gives you the torque. And so that's why we do sine of theta. A lot of times we can ignore the sine theta because we assume that we're applying the force perpendicular to the pivot point, which in this case is here. Notice how F2 is perpendicular to the pivot point, so this would just be F2 times the torque here would be F2 times the radius. You don't have to do sine theta. And Newton's second law, F equals ma, also gets a rotational equivalence. So we just discussed in detail how the rotational mass is I, so you can replace m with I. We've already discussed earlier that linear acceleration equals alpha, angular acceleration, and torque is a rotational force. So Newton's second law rotationally is torque equals tau equals I alpha. That's kind of cool. And just like you can have net forces, you can have net torques. So for example, notice how this force is going to cause it to rotate counterclockwise, and this force is going to cause it to rotate clockwise. So you can define a direction of motion. Maybe clockwise is positive and counterclockwise is negative. So this would be a positive torque, and this F2 would make a negative torque. So when you're defining a net torque, you would subtract these two. And then finally, we got rotational energy. So for example, linear kinetic energy is 1/2 mv squared. So you can replace m with I and v with omega, and you get rotational kinetic energy. So for example, this sphere is going to gain rotational kinetic energy as the rope applies a torque to it. Notice this rope is going to cause it to spin, right? So this rope is, the tension in the rope is your torque force. Torque is going to be F tension times the radius, which is the radius of the sphere here. This pulley is, the tension on the pulley is going to cause the pulley to torque, and the pulley will rotate. This notice neither of these are going to have any linear kinetic energy because they're not moving in a line. Whereas this mass here is going to have linear kinetic energy because it's moving in a line, but it's not rotating, so it's not going to have any rotational kinetic energy. This is actually one of the Webstein problems you're going to be dealing with, so think of these as sort of like hints. When you're using conservation of energy with all this, you'll want to consider the center of mass of the object as the point, the change in height for your gravitational potential energy. So for example, if you have a ruler that is vertical and then it falls down, you want to consider the change, like mgh, right, is your change in gravitational potential energy. You want to consider your h as the change in height of the center of mass. So if the center of mass of the ruler is here, and then by the time it falls it's down here, it's only changed this much in height. So keep that in mind. And seeing how energy isn't a vector, you can actually add linear and rotational energies. So I'm going to give you a big hint for one of your Webstein problems. In this problem, you start off with just some gravitational potential energy, right? And then as m drops, it's going to lose gravitational potential energy. None of these two objects drop, so they don't change gravitational potential energy. Where does this gravitational potential energy go? What does it turn into? Well, it turns into the linear kinetic energy of this one, so you can just go UG of m, little m here, it's going to turn into 1/2 little m v, let's just keep it, I don't want to give you too much of a hint, kinetic energy linear of the little mass plus the kinetic energy rotational of the pulley with the rotational mass of I plus the kinetic energy rotational of the sphere here with mass m. You can add those, even though these two are rotational and this one is linear, they can be added together. All right, that's all I want to talk about for these. I'll do some sample problems, and good luck.